In this video, we're going to look at atomic structure in the A-level syllabus. Now, from the learning outcomes, we can see that a lot of the chapter builds on the what we have already learned in O-level syllabus. For example, if you look at learning outcomes A to E, we have already covered most of it in the O-level syllabus. So if you are still unclear about any of the learning outcomes, I would strongly encourage that you watch the videos on atomic structure for the O-level syllabus before coming to this video. The only slight difference would be learning outcome B, where you have to deduce the behavior of proton, neutrons, and electron beams in an electric field. However, if you look at some higher order O-level MCQ questions, we have already encountered that where we have to recall that based on the charges of a proton, neutron, and electron, you will be deflected towards a plate of the opposite charge. The only slight difference is that in A-levels, now we can determine the angle of deflection. Alright, it's important to remember that the angle of deflection is proportional to the charge and inversely proportional to the mass. Now with this, you can actually do some calculations to determine the exact angle of deflection when given the angle of deflection for one particle. So the only new things that we learn in this chapter would be two new outcomes, which is number one, to write the electronic configuration, all right, given some new knowledge of how electrons are arranged in an atom. Number two is to explain and deduce ionization energies of elements, knowing how the electrons are arranged in an atom. So in this video, we'll look at the first one, how to write the electronic configuration of atoms and ions, given some new knowledge of how they are arranged in an atom. So just a brief recap of what we have learned in O-levels. We have learned the concept of electronic configuration, which is also known as electronic structure. What it means is how the electrons are arranged in atoms. So for example, over here we are looking at chlorine. This is a particular atom of chlorine. So from the representation, we can tell that there are 17 protons and therefore 17 electrons. And in the O-levels, we have learned how to write or how to represent the distribution of these 17 electrons in an atom. All right, we have learned that the electrons are found in electron shells, and the first electron shell can have up to a maximum of 2 electrons, and subsequent electron shells can accommodate up to 8 electrons. So with that, the first electron shell, which is the one that's closest to the nucleus, can only have 2 electrons, followed by 8, followed by 7. Now in A-levels, we're going to learn something extra. So for example, if we look at the 8 electrons in the second electron shell, right, if we zoom in further and we look at these 8 electrons, we'll find that these 8 electrons are further divided into what we call subshells and orbitals. So previously, the concept of electron shells that we have learned in O-levels, they correspond to quantum shells in the A-levels. So earlier we saw that the electronic configuration of chlorine was 2.8.7. What it means is that there are 2 electrons in quantum shell 1, there are 8 electrons in quantum shell 2, and there are 7 electrons in quantum shell 3. Alright, so the concept of electron shells that we have learned in O-levels corresponds to the concept of quantum shells in A-levels. As previously mentioned, quantum shells can be subdivided into subshells and later orbitals. Now this concept may be a little abstract, so I'm going to use an analogy, a very crude analogy, to help you better understand. Now the analogy has to do with the picture that you see. This is an actual photo taken about 10 years ago when I was in Switzerland. I had the fortune to be able to go to Switzerland and to witness skiing on a mountain. So what you see here is a mountain in Switzerland. There are several ski resorts on the mountain. So the analogy goes like this. Now imagine that there are several ski resorts on a mountain. Now the ski resort that's closest to the foot of the mountain is known as ski resort 1. Okay, the next ski resort is known as ski resort 2, and then the following ski resort is known as ski resort 3. Now if you analyze the ski resorts, you may be able to notice that there seems to be a pattern. What is the pattern? Alright, ski resort 1 can only have one story, one level. Ski resort 2, there are 2 levels. Ski resort 3, there are 3 levels. And ski resort 4 can have 4 levels, and so on. So this is one of the pattern that occurs. The second pattern that you may be able to observe is this, that in story 1 of every ski resort there can only be 1 room. Okay, in story 2 there can be 3 rooms, in story 3 there can be 5 rooms, and so on. So how do we relate this analogy, or this ski resort analogy, to subshells and orbitals in an atom? Is this, that the ski resort 1 corresponds to quantum shell 1, ski resort 2 corresponds to quantum shell 2, and ski resort 3 corresponds to quantum shell 3. So your quantum shells are your ski resorts. Now how about the levels? The stories or the levels refer to the subshells. So ski resort 1 or quantum shell 1 can only have one subshell, whereas quantum shell 2 can have 2 subshells, and quantum shell 3 can have 3 subshells. Okay, and lastly, the rooms correspond to the orbitals. Alright, orbital is a very abstract concept. What is an orbital? It's a region in space where you are likely to find an electron. Okay, so in a very crude manner, you can think of them as rooms for electrons, rooms where electrons reside in. Okay, so from the pattern that we have seen earlier, your your first story can only have 1 room. Alright, your second story can have 3 rooms, and your third story can have 5 rooms. Okay, so later we're going to see how your electrons occupy these rooms, following a certain set of rules that you have to remember. Okay, but for now, just remember the analogy. Your quantum shell corresponds to the ski resorts, ski resort 1, 2, 3, and so on. Your level 1, level 2, your floors correspond to the subshells, and the actual rooms corresponds to the orbitals, where it is like a room where you can find a particular electron. So now that we have seen the analogy, let's see how it corresponds to the electronic structure in an atom. So the first thing that we learn is that the quantum shells correspond to the ski resorts. So we can have ski resort 1, ski resort 2, which is higher than ski resort 1, and then ski resort 3, and so on. Alright, next we see that each ski resort have a fixed number of levels or number of floors. Ski resort 1 can have only 1 story or 1 floor. Ski resort 2, 2 floors, 3 floors, and 4 floors correspondingly. Okay, now there's something that we need to learn here, that story 1 in the ski resort, or the subshell, the first subshell, is given a label which we call it the S subshell. So the first story of every ski resort is known as the S story or the S subshell. Okay, with that, I hope you can see that the second story is also given a label. It's called the P story or the P subshell. and then the third story is known as the D subshell, and so on. Okay, it goes on further, the F subshell, the G subshell, the H subshell, but it's not important in the A-level syllabus. Okay, so once again, in a ski resort, in different ski resorts, there are different stories, different floors. The first floor is known as the S subshell. The second story or second floor is known as the P subshell, and the third floor is the D subshell, and so on. Alright, next we also see that at different levels, at different floors, there can be different number of rooms. Okay, in the first story, S subshell, we can only have one room. Okay, in the second story, in the P subshell, there can be 3 rooms or 3 orbitals, and in the D subshell or the third story, there can be 5 rooms, and so on. Again, F subshell is rarely encountered in the A-level syllabus. Okay, so now knowing that each ski resort can have different number of levels, each level can have different number of rooms, we can go on to label the different rooms. Okay, for example, in the first ski resort, right, it can only have one floor, and the one floor can only have one room. So in ski resort 1 or in quantum shell 1, there can only be one orbital, which is the 1s orbital or the 1s room. In the second ski resort, remember there are 2 stories now. There are 2 stories. The first story can have one room only, so we call it the 2s room or the 2s orbital. Okay, and then in the second story, there are 3 rooms. Okay, so we have 3 2p orbitals or 3 2p rooms in the quantum shell 2 or the ski resort 2. For your ski resort 3, first level we can have only one room, second level we can have 3 rooms, and then third level we can have 5 rooms. Okay, and then I'm going to skip ski resort 4 because we will rarely encounter it in A levels again. Now if we learn a little further, we'll find that the rooms in the same level, they are further distinguished from one another. This is based on the direction at which the orbital is pointing at. Okay, but for now I will skip it. So what is important now is to learn a very important rule, which is every room in the ski resort can accommodate only up to 2 occupants, meaning every orbital can only accommodate up to 2 electrons. Okay, and in the world of electrons, the 2 electrons in an orbital must be of opposite spin. I know it's a very abstract concept. In a very crude analogy, every room must be made up of 2 people of the opposite gender. Alright, they are spinning in the opposite direction. Okay, so with that in mind, can you all see that in ski resort 1, it can only accommodate up to a maximum of 2 electrons because there's only one room. Okay, in ski resort 2, there are 4 rooms in total, and each room can accommodate up to 2 electrons. So the maximum occupancy of quantum shell 2 or electron shell 2 is 8. This is what we have learned in O levels. Alright, and in quantum shell 3, if you take a look, we have a total of 9 rooms, 9 orbitals. So quantum shell 3 can actually accommodate up to 18 electrons. Again, in some higher order O-level questions, you may have encountered this, that for example, the electronic configuration of iodine or bromine you would have seen 18 electrons in a particular in electron shell 3. Alright, this is the reason why. Now earlier we have already learned a very important rule in arranging electrons in an atom, which is that each room or each orbital can only house a maximum of 2 electrons, and the 2 electrons must have opposite spins, or very crudely, the 2 occupants must be of opposite gender. Alright, this rule is known as the Pauli exclusion principle at higher levels. Now there are 2 other important rules that you need to take note when assigning electrons to the different ski resorts, to the different levels, and to the different rooms. The first important rule is known as the Outbound Principle, where you always fill up the rooms from the lowest ski resort first, alright, or for the lowest energy first, right? Which makes sense because it takes energy for you to go up the mountain in order to fill up the ski resort. So we always fill up from ski resort 1, and then before we go higher to ski resort 2, and so on. So this is known as the Outbound Principle. The next rule is known as Hund's rule. Now this is something that we encounter when we go up a bus. Alright, when you board a bus, okay, usually each seat, alright, each bus seat can seat 2 passengers. So usually when you go up a bus, I'm sure you will look for one that is not already occupied, alright? Unless you are a pervert or something, you will go for a seat where it's not already occupied so that you have the whole seat to yourself. However, in a case where all the seats are already taken, then you are forced to sit with another passenger on the bus. Okay, this is Hund's rule. So in a subshell, so for example, when you go into ski resort 2, okay, and you are forced to go up to the second level, you would fill up the rooms singly first. You will take up, oh, I have the whole room to myself. However, when all the rooms are already occupied, then you are forced to pair up with another person. So this is known as Hund's rule. Now we see a diagram on the right of the slide. The diagram actually illustrates Outbound Principle. Alright, the arrows from bottom up tells you the order in which we should be filling up the rooms. Right, for example, we should be filling up room 1s first, or 1s orbital, followed by 2s orbital, the second arrow. And then next, the third arrow, we will fill up 2p, followed by 3s, and then 3p. Alright, I know it looks slightly contradicting to Outbound Principle, that we fill up 4s first before 3d, but this one I will explain later on in the video. Okay, so once again, the diagram that we have just seen illustrates Outbound Principle. The arrows tell us the order in which we should be filling up the orbitals or the rooms. The diagram below it can be used to illustrate Hund's rule, alright, which as well as Pauli exclusion principle, which is what I'm going to show you now. So over here we see a P subshell. Earlier I've already mentioned that the 3 rooms in story 2 can further be distinguished based on the orientation of the orbital. So for example, there are 3 rooms in story 2. The 3 rooms are distinguished as Px, Py, and Pz. Alright, this is within the syllabus, but I'm not going to go too much into it. So p orbitals, they look or s orbitals have a spherical shape, okay, x, y, and z. Alright, p orbitals have a dumbbell shape. So the orbitals that are oriented along the x-axis will be known as your px orbital. The orbitals that are oriented along the y-axis will be your py orbitals, and the orbitals that are oriented along the z-axis will be your pz or pz orbitals. So the 3 rooms on story 2, or the 3 orbitals in your p subshell, can be further distinguished as px orbital, py orbital, and pz orbital. Okay, so I'm going to illustrate Hund's rule now. if I want to fill up the p subshell, I will fill up singly first. Okay, so for example, if I need to assign 2 more electrons, I'll assign them to the empty py orbital and the empty pz orbital instead of pairing up in the px orbital first. Okay, now beyond that, if I need to assign any more electrons, then I'm forced to assign the next electron to your px room, because all the orbitals are already filled up. So now I will have to fill up in this particular order. Okay, so 2 things to take note. Number 1, we always fill up the orbitals in each subshell singly first before pairing them up. And when we pair them up, notice the symbol that I'm using here. Each electron is represented by a half arrow. Alright, and how do I show that they have opposite spins? Is that one of the electron has the arrow pointing up and the other one has the arrow pointing down. So this shows that the 2 electrons are of opposite spins. So right now I'm going to use the analogy to write the improved or the enhanced electronic configuration for our chlorine example. Okay, so we have learned that chlorine in secondary school. We have learned that chlorine has an electronic configuration of 2, 8, and 7. What it means is that we have 2 electrons in the first electron shell, 8 in the second, and 7 in the third. So in our improved enhanced definition, what it means is that there are 2 occupants in ski resort 1, there are 8 occupants in ski resort 2, and there are 7 occupants in ski resort 3. Okay, recall that each electron shell corresponds to a quantum shell and each quantum shell corresponds to a ski resort. Okay, ski resort 1 has only 1 story, 1 subshell, and story 1 has only 1 room. So these 2 electrons are actually found in your 1s room. Okay, next, the 8 electrons that are found in ski resort 2. Ski resort 2 has 2 levels or 2 subshells, your 2s and your 2p. So your 2s will fill up 2s first because story 1 is lower than story 2, and story 1 can only have 1 room, so we have only one 2s orbital which can accommodate 2 electrons. And then after that we have 6 more electrons. These 6 electrons have to go up to second story. Second story, there are 3 rooms. Okay, so 3 rooms can accommodate up to 6 electrons or 6 occupants. Okay, then in quantum shell 3 we have 7 electrons. In quantum shell 3 there are 3 levels, so we'll fill up the story 1 first. Story 1 again has 1 room. Alright, and then before we fill up story 2 or your p subshell, which has 5 more electrons. So that. Okay, so a chlorine atom at A levels, if we write the enhanced or the improved electronic configuration, we are supposed to write it like that. Instead of 2, 8, and 7, we are supposed to show further how each electrons are further assigned to the different orbitals. Now with the analogy at the back of our mind, let us try to write the electronic configuration for calcium atom. At O levels, we will simply represent it as 2882. Now we will see how we can expand this 2882 arrangement into further subshells and orbitals. For that, we're going to make use of the diagram on the right to tell us the order of orbitals to fill up. And the all-important rule to remember in A levels is that we always fill up the 4s orbital before the 3d orbitals. I repeat, when writing electronic configuration for atoms in A level, alright, we will always fill up the 4s orbitals before the 3d orbitals. Now the reason for that, we will not go into it in this video. If you want, you can search for it on the internet. There are many explanations for that. Alright, just remember 4s before 3d. Okay, so how do we fill up the 20 electrons in calcium? We'll start with the first orbital. The first orbital is your 1s orbital, which can accommodate up to 2 electrons. Then we go on to the second ski resort, or quantum shell 2, where we start at story 1, so 2s orbital, 2s2, and then we go on to story 2, or p subshell, 2p6. Okay, then we go on to the third ski resort, 3s2, 3p6. Okay, and then after p orbital, remember after 3p orbital, after filling up your 3p subshell, we will go straight to 4s first, so 4s2. Okay, so how does this enhanced electronic configuration correspond to what we have learned in O-levels? Is this 1s2 corresponds to the first quantum shell, alright, 2s2 2p6 corresponds to the second quantum shell, 3s2 3p6 third quantum shell, and 4s2 represents the fourth quantum or electron shell. So what we have seen so far is how we write the enhanced electronic configuration to show the fine division of electrons, not just in quantum shells, but according to different subshells, and then finally different orbitals. Okay, and the key thing to remember would be your 3 rules, your Outbound Principle. We always fill up from the lowest energy orbitals first. Okay, your Hund's rule, in a particular subshell we always fill up singly before pairing them up. And then lastly, your Pauli exclusion principle, where in each room or in each orbital your electrons must have opposite spins. Now things get a little bit complicated when we look at the electronic configuration for transition metal atoms, which we'll see in the next video.